In this last video, we're going to take a look at how substitution occurs on benzene rings that have more than one substituent. We've learned that certain substituents are activating groups, meaning they make a benzene ring more reactive towards electrophilic aromatic substitution. And we've learned that other substituents are deactivating groups, meaning they make a benzene ring or an arene less reactive towards electrophilic aromatic substitution. We've also learned that groups are able to direct substitution onto specific positions around the ring. And so this story, you might think, might get a little more complicated if there is more than one substituent on the benzene ring when we try to do electrophilic aromatic substitution. But in reality, it's pretty simple. So here are several different reactions that we're going to take a look at. If you want, pause the video and draw out these schemes. As you can see, I'm not showing any change to the product. That's what we're going to go over in this video. But you can draw out these schemes and get them into your notebook so that you can follow along more easily with the video. So in this first reaction, if you look, we have two substituents on our starting material. And these two substituents, one of them is a hydroxy group, right? And we know this as an electron donating group. So that is going to activate the ring. The other is a formal group, or an aldehyde, and this is an electron withdrawing group, right? So we know electron withdrawing groups deactivate the ring, right? We also know that electron donating groups are going to direct substitution into the ortho positions and the para position. Electron withdrawing groups are going to direct substitution into the meta position, all right? So in this case, we cannot do para substitution relative to the hydroxy group. So when electrophilic aromatic substitution takes place, we can add an electrophile to one of the ortho positions, right? Or we can add an electrophile to both of the ortho positions. Whether we add an electrophile here or here, it's going to give us the same exact molecule, and that's why we're only showing one monosubstituted product. All right? So what we want to take away is that the electrophilic aromatic substitution occurred ortho relative to the electron donating group, meta relative to the electron withdrawing group. That should be as expected. If we take a look at the second reaction, now we have a meta relationship between the hydroxy group and the aldehyde. So when electrophilic aromatic substitution takes place, right, it can take place in one of four positions. It can take place here, which has an ortho relationship to both the electron donating and withdrawing group. It can take place here, which has a para relationship to the donating group and an ortho relationship to the electron withdrawing group. Substitution could take place here, which is meta relative to both the donating and withdrawing group. Or substitution could take place here, which is ortho to the donating group, para to the withdrawing group. Well, the three products that we are going to form, one is going to have that electrophile, not the bromine, the electrophile ortho to the hydroxy group. Another product will put that electrophile para to the hydroxy group. And then the third product, we're likely to see some poly substitution, right, because we have an activated ring. One thing you notice is that we're not getting any product, any substitution to occur meta relative to the electron withdrawing group. And I think this really illustrates the impact that electron donating groups and electron withdrawing groups have on a benzene ring. And really what we want to take away from this is that whenever we're doing electrophilic aromatic substitution on a benzene ring with an electron donating and an electron withdrawing group, the electron donating group is going to be the group that dictates where the substitution occurs, right? Because that is the group that can put electron density into the ring, make some positions more nucleophilic than others, and also stabilize the rhenium ion for, in this case, the ortho and para pathways. Right? So when we're looking at these systems, the electron donating group will determine reaction rate and regioselectivity over the electron withdrawing group. right? So in these cases, the electron withdrawing group doesn't really matter. I mean, it matters in that we can't do para substitution here, right? We can't do meta substitution here, right? But that electron donating group is not dictating where substitution will take place. It's really only the electron donating group that determines where the substitution takes place and how fast that substitution is going to occur. Right? Now, granted, a phenol with an electron donating group on it is going to be slightly less active than just a plain phenol, but it's still going to be an activated ring. We would still consider this an activated ring. Right? So that's the story whenever we have both an electron donating and an electron withdrawing group on these rings. Now let's take a look at what happens when we have two electron donating groups, right? So if we look at this third reaction, we have an amino group and we have a methyl group, all right? The amino group, remember, has a lone pair of electrons. This AC is just an acetyl group. I wanted to abbreviate it rather than drawing out the full structure. Remember, the acetyl group, when on a nitrogen, is going to reduce the electron donating ability of that nitrogen. Right? Not stop it, but just reduce it. All right, so we have two electron donating groups, and now we have to think about which of these two electron donating groups is going to be the stronger electron donating group. Well, in this case, we can generalize and say electron donating groups that have actually put a pair of electrons into the ring, can conjugate with the ring. Those are always going to be the stronger electron donating groups. So in this case, the amino group is going to be a stronger electron donating group than the methyl group. As such, when the electrophilic aromatic substitution takes place, it will take place in the ortho position relative to the stronger electron donating group. So in this case, if we have two electron donating groups on the ring, it's always going to be the stronger electron donating group that determines the reactivity, the overall reactivity, and also the regioselectivity, right? So again, the amino group in this case is the stronger, or the group that better stabilizes an rhenium intermediate. In this fourth reaction, right, now we have a case where we have two electron withdrawing groups, right? And in this case, no reaction is going to take place, right? Once we get kind of a critical mass of electron withdrawing groups onto a benzene ring, we're just pulling so much electron density out of that ring, right? And forming and making really, really high energy rhenium intermediates that no substitution can really take place. So we don't really have to worry about systems that have multiple electron withdrawing groups on them, because subsequent EAS is just going to be so slow. So we don't need to worry about figuring out where substitution will take place in this case. Finally, I want to take a look at a system that has more than just two substituents on a benzene ring, and really try to take a close look at where substitution will take place. So as you can see on this molecule, we have two electron donating groups, so these are both methoxy groups, and then we have an electron withdrawing group. So let me highlight these electron donating groups in blue and electron withdrawing group in red. Now let's go around the ring and take a look at each position. So remember, we said that whenever we have an electron donating group and an electron withdrawing group on the same ring, it's always going to be the electron donating groups which determine the selectivity of substitution. So when we look at this, right, we have an ortho relationship between the two methoxy groups. So if we do substitution in this position, will be ortho to one methoxy group, but meta to another methoxy group. If we substitute in this position, we'll be para to one methoxy group, but meta to another methoxy group. And if we substitute in this position, we'll be ortho to one methoxy group and meta to another methoxy group, right? So there's really no position that is going to be activated by both of these methoxy groups. And hopefully we can understand that by the fact that they have an ortho relationship in the starting material. So when we look at this, it's not completely clear where substitution is going to take place. And if we do any electrophilic aromatic substitution, we're likely not going to get just one product. However, when substitution does take place, substitution would take place mostly in this position that is para to one methoxy group, meta to the other methoxy group, and then ortho to the formal group or to the aldehyde that's on the ring. I want you to pause the video and think about why substitution occurs here, or why this is the major product of an EAS reaction from this starting material. So if you pause the video and thought about it, hopefully you can see how the substituents around this benzene ring are distributed. If we were to put an electrophile in this position, we would have three substituents all in a row, all on one side of the ring. And that's going to be sterically unfavorable. So it's going to be a little harder to substitute in this position because we're going to have three substituents all in a row. Likewise, if we put a substituent here, then we're going to have 1, 2, 3, 4 substituents all in a row around the ring. And that is certainly going to be more sterically crowded than putting a substituent in this position here, right? Putting four substituents in a row, trying to do substitution between two other groups is going to be very difficult, right? So even though we can't really identify a position that's electronically better, one position that's electronically better than the others, right? We can identify a position that is sterically better than the others. So in this case, the substitution at this position is best for sterics. Right? We can say that all three positions that we identified are going to be equal electronically, right? Meaning that they're going to be at least, each of those positions is going to be stabilized by a methoxy group, right? But only this position is going to allow us to spread out those substituents over the ring. Right? So if we take a look back at this reaction here, you'll notice that when electrophilic aromatic substitution took place, even though this is ortho to the hydroxy group, we did not substitute in this position. So the reason why substitution would not take place here is because of the higher steric strain. Right? And the steric drawback of having three substituents all in one row. So when substitution takes place here, it'll be on one ortho position relative to the hydroxy group, para position relative to the hydroxy group, or we'll get disubstitution. But we would not expect a significant amount of product where the electrophile ends up in the other ortho position, or ortho to both of those substituents. So this finishes off the chapter on electrophilic aromatic substitution. In the next chapter, we're going to be looking at how we can add nucleophiles to benzene rings to also affect substitution.